Okay, let's just jump right into this explainer. For centuries, you and I, and well, all of physics, have relied on this really quiet, comforting assumption about how the universe works. We assume things exist independently, right? And that they influence each other in perfectly predictable, logical ways. But as we're going to see today, the microscopic universe, yeah, it operates on a completely different, almost terrifying set of rules. Rules that absolutely shatter our everyday intuition about what reality actually is.
To really set the stage here, we have to look at this famous warning from Nobel laureate Richard Feynman. He basically said, if you think you understand quantum physics, you don't. And that's not him being arrogant. It's arguably the most successful scientific theory we've ever had. I mean, it literally powers the computer you're using right now. Yet, at its core, it introduces concepts so profoundly bizarre, they genuinely challenge the way our human brains are wired to perceive existence. Let's contrast this for a second. Think about the classic Clockwork universe of Isaac Newton. In that classical world, a car is strictly moving or it's at rest. It has a definite position, a definite speed. Makes sense, right? But the quantum realm is entirely different. Down at the level of atoms, reality isn't made up of solid, localized things. Instead, we're dealing with these weird, abstract, unresolved waves of probability. It's fundamentally random.
And the absolute gateway to all this weirdness is a little concept called superposition. So before you actually measure a quantum particle, it doesn't have a single fixed property. It just doesn't. It literally exists as this massive range of all possible outcomes simultaneously. And the crazy part? It's not just that our human tools aren't good enough to see it, it's that the particle itself fundamentally hasn't decided what it is yet.
Think of a spinning coin. While it's flipping through the air, it hasn't settled on heads or tails, right? It's just this blur of both. Or, take Schrödinger's completely iconic, if slightly morbid, thought experiment. You've got a cat in a box with a random deadly trigger. Until you actually open that lid and look inside, that cat exists in a mathematical state of being both alive and dead at the exact same time. At the quantum level, electrons literally live in this bizarre, unresolved dual state naturally.
Which brings us to the absolutely legendary double-slit experiment. This is the ultimate proof of particle-wave duality. Imagine firing paintballs at a wall that has two vertical slits in it. You'd expect to see exactly two distinct columns of paint on the wall behind it, right? Of course, but when physicists fired individual, solid electrons at two microscopic slits, they didn't get two bands. No way! They got a massive, complex pattern of overlapping stripes, meaning somehow each single electron was passing through both slits at the exact same time as a wave and actually interfering with itself. And here is where things get truly, undeniably spooky. It's called the measurement problem. If we decide to place a tiny detector right at the slits just to see which one the electron actually goes through, it instantly stops acting like a wave. Just like that. It snaps back into being a solid particle, and we suddenly get those two boring bands on the back wall. Literally, the mere act of observing it causes the wave function to collapse. Why does simply looking at a system force reality to pick a definite state? Well, honestly, physics still has giant holes trying to explain that one. Now, if you think a single particle doing this is weird, just wait until two of them meet. Welcome to quantum entanglement. Under the right conditions, two independent particles completely lose their separate identities and merge into one single shared wave function. So if you measure one of them, you instantaneously determine the exact state of the other one, and it does not matter how incredibly far apart they might be. Now, you might be thinking, okay, so what? Like if you order a burger and a hot dog in two identical fast food boxes, opening one and seeing the burger instantly tells you the other box is the hot dog. Sure, but that's classical mechanics. The food was already predetermined before you looked. Entangled particles? They have absolutely no hidden labels. Both boxes contain a completely unresolved blur of both the burger and the hot dog, right up until the very millisecond you open one of them. This whole idea deeply, deeply troubled Albert Einstein. He just couldn't accept that measuring an electron right here on Earth could instantaneously force its entangled partner, which could be billions of light years away in the Andromeda galaxy, into the opposite state, with zero delay. To him, that smelled exactly like faster-than-light communication, which his own theory of relativity strictly forbids. He famously, and kind of mockingly, called it spooky action at a distance. What entanglement is really attacking here is the absolute foundation of our sanity, a concept called local realism. This is that comforting, everyday assumption that, hey, the moon is still there even when I'm not looking at it, and that physical influences, like a radio signal or gravity, actually take time to travel through space. Well, quantum mechanics came along and threatened to completely throw both realism and locality straight out the window. And this tension led to the ultimate heavyweight physics showdown in 1935. In one corner, you've got Einstein, arguing that particles simply must carry predetermined, hidden variables, basically secret pre-programmed instructions that preserve the normal rules of space and time. And in the other corner, Niels Bohr, aggressively pushing back. Bohr claimed it is fundamentally meaningless to even talk about a particle having a definite state before it's actually observed. And for decades, this was just a purely philosophical stalemate.
But that debate finally got unstuck in 1964, when physicist John Bell did something absolutely brilliant. He took this high-level philosophical conflict and translated it into a strict mathematical limit, which we now call Bell's inequality. He realized, look, if Einstein's hidden variables actually exist, they can only produce experimental correlations up to a very specific numerical limit. But if Bohr was right, entangled particles would blow right past it. Suddenly, this wasn't just coffee shop talk anymore. It was an empirical test you could actually run in a lab.
So they ran the tests. In the 1970s, scientists fired up these highly precise experiments, and the results were earth-shattering. Every single refined test consistently violated Bell's inequality. So, spoiler alert, Einstein was wrong. Pre-programmed hidden variables do not exist. Particles truly, genuinely do not have defined properties until you measure them, and the universe is proven to be fundamentally non-local. At the quantum level, physical separation is just an illusion.
Which naturally brings up a massive cognitive dissonance for all of us, right? If the universe is fundamentally this non-local, unresolved, weird place, why does our everyday world look so predictably normal? If everything is made of these probabilistic, entangled waves, why doesn't my coffee cup suddenly exist in two places at once? Why don't I just quantum tunnel right through my chair right now?
Well, the answer to that is a process called decoherence. Think about trying to hear your friend whisper to you in a totally packed, incredibly noisy room. The original signal is technically still there, but it gets completely overwhelmed by all the chaotic noise. Because everything in our macroscopic world is constantly interacting with a noisy environment, like trillions of air molecules bouncing around, that delicate quantum superposition spreads out rapidly and basically just washes out. It averages out into the stable, solid, boring behavior we see every day.
So what this teaches us is that the classical, solid reality we live in isn't false, exactly, but it's an emergent layer. It's a simplified approximation. Down at the deepest, most fundamental level, the universe isn't a collection of isolated objects interacting across empty space. It is a massive web of deeply interconnected, continuous relationships. The objects we see are just derived from how that complex system is observed.
But here is the really cool part. We aren't just passively observing these strange laws anymore. We are actively harnessing them. When scientists figure out how to isolate systems and prevent that environmental decoherence, the resulting technology is mind-bending. We're talking about atomic clocks using entangled systems to measure time so perfectly they wouldn't lose a single second in billions of years. Or quantum cryptography, which distributes tamper-proof keys. If a hacker even looks at the photon stream, the wave collapses, the data is scrambled, and they are instantly exposed. It's incredible.
So, let me leave you with this one final, reality-breaking thought to chew on the next time you look up at the night sky. If space doesn't fundamentally separate entangled particles at the quantum level, then maybe distance itself is just a useful illusion, just a handy shortcut our human brains evolved to use so we can navigate a universe that is, at its very core, profoundly and wonderfully interconnected. Keep that perspective in mind today. I really hope this explainer has completely shifted the way you view the reality around you.